Bom dia. My name is Robert Bryant from Duke University in the United States. It's my pleasure to introduce our speaker this morning. Alexander Lubotzky is the Maurice and Clara Vey Professor at the Einstein Institute of Mathematics of the Hebrew University of Jerusalem. He is known for his many contributions to geometric group theory, the study of lattices and Lie groups, representation theory of discrete groups and Kazhdan's property T, the study of subgroup growth and applications of group theory to combinatorics and computer science, notably expander graphs and error-correcting codes. He received his PhD in 1979, working under the direction of Furstenberg, and in the nearly 40 years since, he has made profound contributions to the mathematics of geometric group theory, and for which he has received many awards, including the Landau Award, the Bergman Memorial Prize, the Erdős Prize, the Rothschild Prize, and just this year, the Israel Prize, just to name a few. He has visited many of the most prestigious mathematics institutes in the world and has delivered dozens of distinguished invited lecture series. It's a pleasure to welcome him to the stage where today he will give us a talk entitled High-Dimensional Expanders. Professor Lubotzky.
Thank you very much. Thank you very much for the introduction. Thank you very much for the invitation and the opportunity to speak here. It's a big honor, and also it's a quite unique opportunity to present to a general audience the subject of high-dimensional expanders. In order to start, I must start with a crash course of few minutes on a subject which got a lot of attention in the last 5 decades, the so-called expander graphs, so that we will know what we want to do when we talk about high-dimensional expander. So let's talk first about expander graph. So expander graph, maybe, I don't know if it's seen here, or maybe better here. Is it visible when I do it here or not really? The pointer. It's okay? Okay, I'll try to do both. So let X, V, E be, be a finite graph. Usually we want a k-regular graph, namely the degree of every vertex is exactly k. K is a fixed positive natural number. And we define the Chigger constant of the graph to be the minimum over all proper subsets of the graph V, which are not empty and not the full graph, when we take the number of edges going from W outside W, going from W to the complement of W, and we divide it by the minimum of the size between W and W complement. If we let's make it simpler, if we take W to be, say, at most half of the size of the graph, to say that the Chigger constant is large if every set W, there are many edges going out of it, going out of W. Now you can imagine that why such an invariant is important in computer science. When you want to make you want to take a graph that will be very, very much connected, then of course the best graph will be the complete graph. But the complete graph on n vertices as n choose 2 edges, namely quadratic in the number of vertices. The name of the game here is to try to get graphs such that the number of edges is only linear in the number of vertices, and still they are very connected, like the complete graph in some sense. And the technical term is this Chigger constant, which should remind those of you with some experience in Riemannian geometry, the Chigger constant in Riemannian manifold, which is exactly the analog of that, or more precisely, this is the analog of the Cheeger constant of manifold. And the graph is called epsilon expander if its Cheeger constant is at least epsilon. Now, this type of object are extremely important in computer science. And again, you can imagine why. We want to have a network which is very connected, but we don't want to pay the price of having all the edges. For example, think about kind of a future supercomputer with a lot of small microprocessors who should talk to each other. So the best will be if we put 10,000 microprocessors and each one will be connected with each other. But then we need millions of connection. But if I allow you to connect every microprocessor to only 15 others, so I'm getting a k regular graph with k equal 15, and I want it to be very connected. And this is the notion of expander. Now, it's not even clear that such expander exists. Now, when we say exists, we don't mean about one. We mean always k fixed. The size of the graph is going to infinity, and epsilon is the same epsilon for all the graphs in the family. Pinsker was the first one to prove, like 50 years ago, that random k-regular graphs are expanders. So great, which means that almost every graph, k-regular graph that you will choose will be such an epsilon expander, but it's a non-trivial issue to check if it is indeed an expander. The first explicit construction was made by Margulis, who used for that Kashdam property T. So what really proved that if gamma is an infinite discrete group generated by finitely many elements and has Kashdam property T, then the family of Cayley graphs of the finite quotients of gamma form a family of expander. If you know what is Kashdam property T, fine. If you don't know, maybe even better, because don't confuse yourself now with technical details. The point of the work of Margulis, and this was a big breakthrough, by now the standard, this is a simple proposition. If I would have time, I could give you the full proof, but the point here is that he made the first connection with our subject, with kind of down-to-earth combinatorics, with the fancy theory of representation theory of Lie groups. So it's kind of amazing that the first construction of this finite object use, a representation of semi-simple Lie groups on infinite-dimensional Hilbert spaces. And this was extremely influential work, which led later on to some of the development that I'm going to describe. But before that, let me say that the whole area turns out to be very much related to the subject, to the story of spectral gap. This, again, those who are familiar with the story with Riemannian manifold are maybe not so surprised. It's just like the Cheeger inequality, which relates this Cheeger constant to the spectral gap in eigenvalue of the Laplacian of the manifold. There is an analog theory here for graph, and basically expansion is the same as spectral gap. What I mean here by spectral gap, if A is the adjacency matrix of X, by this we just mean X is a finite graph with n vertices, so just take the n by n matrix and put 0 or 1 if you have an edge or not between point I and point J. We get a matrix. It's easy to see that the largest eigenvalue of such a matrix, if it's a k-regular graph, is going to be k. Minus k will also be an eigenvalue if and only if the graph is bipartite. So these are for us the two trivial kind of eigenvalues. And the graph is expander if and only if the second largest eigenvalue. See, this is a symmetric matrix, so all eigenvalues are going to be real numbers, all of them between k to minus k. And the graph is expander if and only if the second eigenvalue is bounded away from the first eigenvalue along the family. And basically what we want to bound the non-trivial eigenvalue to be as close as possible to 0. Again, it's a simple exercise about Markov chains to see that if the eigenvalues are concentrate around 0, then the random walk on that graph converges just very fast to the uniform distribution. So again, this is another hint why this notion of expander is so important in computer science. So we want to do them as close as small as possible. The Alombo-Pana proposition tell you that there is a limit to what you can do. At least if you want an infinite family of k-regular graph, the best bound you can opt for is 2 square root of k minus 1. You cannot do better than bounding the eigenvalues by 2 square root of k minus 1. Okay, that's bad news, but also, I mean, 2 square root k minus 1 is much smaller than k, so we can still opt to do it. And let's give a name now, which is, I don't have time to explain where the name comes from, but let's say we will call the graph Ramanujan if indeed all the non-trivial eigenvalues are bounded by 2 square root of k minus 1. So in a way, Ramanujan graph, if exists at all, which is highly non-trivial question, if they exist, are going to be the best possible expander, like the one on which the random walk converges fastest to the uniform distribution. And now the connection, which really was kind of shown by Margulis between representation theory and graph theory, led later on in the 80s to the construction of Ramanujan graphs. Now, the construction is quite fancy, and I cannot really go too much into details. Let me just say, throw some words in a little formal way. The way these graphs are constructed is the following. We look at fields F, like the p-adic numbers, or the formal Laurent power series over the finite field of order P. These are kind of a locally compact, non-Archimedean fields. We look at the group PGL2 over that field, or PSL2, whatever you prefer, it doesn't really matter. We divide it from the left by a maximal compact subgroup K. Let's stop for a minute and think. If we take a more familiar situation where the field is the field of real numbers, and we look at PGL2R, and we divide it from the right, not from the left, sorry, by K, by the maximal compact subgroup, we get the upper half plane, the two-dimensional hyperbolic plane. And then, on the other side, you divide it by the action of a discrete co-compact subgroup. If you do it over R, you get Riemann surface. And in fact, all Riemann surfaces of genus greater or equal to are obtained like that. Amazingly, if you do it over the p-adic numbers, what do you get? Well, we want to say that we get p-adic Riemann surfaces. But really what we get, just finite graphs. Because of the Bois-Titz theory, the Bois-Titz theory tells us that this PGL2F over K is in a somewhat natural way, maybe not so natural before you learn the theory, but natural after you learn the theory, as a structure of a P+1 regular tree. So now if you have a regular tree, you divide it by the action of the group, you get a finite graph. It's finite because the discrete group is co-compact, so you get a graph which is compact. Discrete plus compact means finite. You get a finite graph. Well, let me just warn you to be careful. You may say, oh, these are your Ramanujan graph. Not quite, because every finite p plus 1 regular graph is obtained like that, and not all of them are Ramanujan. But if you make a very special choice of your discrete group and you take it to be a congruent subgroup of an arithmetic group gamma, again, if you know what does it mean arithmetic group and what does it mean congruent subgroup, fine. If you don't know, even better, because the only reason to put these words here is to hint that there is a deep connection with number theory here. It's only by some very special choice of groups that we do get a Ramanujan graphs, and the proof that the graph obtained this way are indeed Ramanujan is based on a very deep work of Deligne, who proved the Ramanujan conjecture in characteristic 0, and Drinfeld, who proved the Ramanujan conjecture in characteristic P. So somehow you start to smell why these graphs are called after Ramanujan. So there have been some works like that by Margulis and Philip Sarnak and me and my student Morgenstern, various construction, all based on this structure. Okay, this we should run just very quick history of the expander. So expander, the first construction, as I said, was by Pinsker, not construction, by Pinsker, who showed that random K-regular are expanders. Then Margulis by property T. Then the Ramanujan graphs by Margulis and also by Philip Sarnak and mine. More elementary constructions, the so-called zigzag product, were done later on by Reingold, Vadaan, and Wigderson, and still it has been an open problem for a long time whether for every K you can get such Ramanujan graph, and this was solved recently by Marcus Spillman and Srivastava by a new technique called interlacing polynomials. But these are non-constructive methods. These are existence, not random, but not constructive. It's an interesting story by itself. Anyway, in most applications, what we really want is K-regular graph, K peaks, and epsilon going to infinity. But let me now, it already took me more than I planned, or maybe just finish this to say that expanders are extremely important in computer science and combinatorics, and in the last decade, they found also many applications in pure mathematics. There is a very good survey by Khoury, Lineal, and Wigderson about the application in computer science, and a much less good survey by me on the application in pure mathematics in the bulletins of the AMS. And really, expanders are extremely important. If you hit Google, write expander and hit Google, you get 4 million websites mentioning expanders, but don't be too impressed because most of them are about expanders of dentists. So, and only maybe 3% are about expanders in mathematics, which really should maybe teach us to be a little bit modest when we talk about our object as extremely important and the rest of the world. It looks like these expanders are more important for humanity than our expander. Anyway, let me jump now very quickly to our main subject, and this is the I-dimensional expander. Now, what we mean by I-dimensional here, we want just to replace the graphs by I-dimensional objects. Now, you can talk, if you want, about the computer scientists like to talk about hypergraphs. Mathematicians maybe prefer simplicial complexes. They are basically the same thing, especially if you take what is called uniform hypergraph, which means you take set V and you take a collection of subset of size D plus 1. So, you know, if D is equal 1, D plus 1 equal 2, then you get a graph. You can think of it as a D-dimensional pure simplicial complex, which means you take a collection of subsets of V, which is closed under inclusion, but all maximal faces are of size d plus 1. So basically, this is exactly the same object, like hypergraph, just that we think about it, that we take all the subsets also as faces. And so we can talk about edges, triangles, etc., etc. Now, before I go ahead, just everyone maybe want to try to think for a second. If I will ask you, find what is the definition of I-dimensional expander. How we take this property of being expander and to the I-dimensional world. What will be even the definition? I had to say, and I didn't say, I mentioned about expander two aspects, the expansion and the spectral gap. But in fact, one can give dozen, I'm not exaggerating, of equivalent definition of expander, and the beauty of the subject comes from the fact that all these different definitions are equivalent to each other. Each one of these definitions, you can suggest some extension to the higher dimensional case, and sometimes even more than one. So we get really a lot of options to what should be called high-dimensional expander. And so if you would ask me what is high-dimensional expander, the honest question would be, I don't know. The non-honest question would be that there are many options. And they are not all equivalent to each other, and the whole area is still in the stage of formation that we are not completely sure what eventually will be the right definition, if there is a right definition. Anyway, in a kind of a strange way, the Ramanujan, which is the most difficult kind of subject within expander graphs, it's kind of clear how to generalize it to I-dimensional. Why? Because you see, you remember, or at least the construction is clear. Why? You remember, I talked with you before about the construction of Ramanujan graphs as PGL2 over a local field F divided by a maximal compact subgroup on one side, dividing by an action of a congruent subgroup of an arithmetic group from the other side. Anyway, something very fancy, but kind of a clear object which give you a graph. If you change the 2 to PGL D plus 1 F, the same Brouwer-Tietz theory that I described you before, I just mentioned before, teaches us that PGL D plus 1 F modulo maximal compact subgroup, the analog of symmetric spaces in the case of Lie groups, give you a contractible infinite simplicial complex of dimension D. So if we go and we divide it from the other side by congruent subgroups of arithmetic group, just like what we did in the case of D equal 2, in PGL2, we will get finite simplicial complexes, and we would love to think of them as Ramanujan complexes, like high-dimensional versions of the Ramanujan graphs. What enabled really to do this was really the work of Laforgue. Not Laforgue, who will speak here in a day or two, but his brother, Laurent Laforgue. Laurent Laforgue got the Fields Medal in 2002 for exactly extending the work of Deligne, or more precisely the work of Drinfeld, about the Ramanujan conjecture from PGL2 to PGLD. By the way, for the young people, you should notice that everyone who worked for us got the Fields Medal. So if you want to choose your area of research, better do something for us. So now, once he did it, it became kind of clear that there should be a theory, there should be some, even though his work was very abstract on automorphic forms and algebraic geometry, etc., there should be some down-to-earth application of his work by a construction of Ramanujan complexes. And indeed, a few of us, Lee and Beth Samuel and Vishna and I at Yale, I must mention the name of Beth Samuel, who was a student at Yale at the time. And in fact, she was a student of Yatetsky Shapiro, and she came to me and said, well, I learned automorphic form, but I'm a bit stuck, but maybe you can suggest me something to work on. I told her, you know, I don't know much about it, but Laforgue proved this. There must be some combinatorial meaning of his work. Let's work on it. And indeed, we work. It turns out to be a fairly complicated work. And the tragedy is that 2 years after she finished the degree, she passed away. She had a very, very serious cancer, and she left 2 babies. It was really a big tragedy. Moreover, you know, when we did this work, it was published, but in a way, nobody paid attention to that, because I have to admit that the whole idea to work on that was in order to have a thesis, you know, that you'll have a subject for a thesis. But gradually, an application has been found, and in some sense, some of this lecture will be dedicated to them. I must say that nobody paid attention to our work except of the Indian government. Our paper was called Ramanujan Complexes, and the government of India even called the neighborhood there Ramanujan Complex after our paper. What is even more impressive, that they did it 15 years before we wrote the paper. They already predicted that there will be such an important paper, and they called some scientific center in India by the name Ramanujan Complex. Anyway, this is few words about Ramanujan complexes. And just like in a show of Brecht, you say in English, if you see a pistol on the table in the first scenario, it will appear again at the end. Let's forget about it. It will come back, and let's ask ourselves, what is I-dimensional expander? And as I said, there are a good number of suggestions. I don't have time to present you all. I have only time to present you one, and I chose to take an approach which was led by Gromov, because this is something which is the most visible and really beautiful and kind of amazing. But there is a story here, so I'm starting now a third crash course, which on the beginning will not be at all connected to the subject that we study so far, and eventually all this will be connected. The story is about a theorem of Borosh and Furedi from '84. Borosh and Furedi at the time were 2 young undergraduates in Budapest who proved the following beautiful theorem as an answer to a question posed by Erdos. They proved that given a subset P of R square of size n, you take in the plane any set you want with n points. Now, if you have n points, then they determine n choose 3 triangles. And then just draw all the possible triangles between these n points. You get n choose 3 triangles. Then they prove that there exists a point which is covered by 2/9 of them. 2/9 of the n choose 3 triangle meets somewhere. Okay, beautiful result. The 2/9, by the way, is the optimal. This was proved later on. Shortly after that, Bharani proved the I-dimensional version of this theorem. Now, what is the I-dimensional version of this theorem? namely fix d, now d will be the dimension, fix d, for every d, there exists a positive constant cd such that if p in R to the d is a set of size n, now, given any set of size n in R to the d, we have n choose d plus 1 simplices determined by that set of n point. So at least CD of them intersects. Namely, there is a point which is covered by at least this fraction of them. Well, this is the generalization of the Borosh-Furedi theorem to higher dimensional. Around 10 years ago, Gromov came into this subject and completely changed the perspective of the subject and proved an amazing result. Before I will tell you what is the amazing results of Gromov, let me give a definition. Then it will be easier to formulate the result. And the definition is the following. Let X be a d-dimensional simplicial complex. We say that X has the geometric, respectively topological, epsilon overlapping property if we have the following property. For every map from the vertices, x0 is the set of vertices of the simplicial complex. We start with a map from the vertices to R to the d, and then we take any affine extension. Well, there is a unique affine extension, right? If I have a map from the vertices of a simplicial complex to R to the d, then the straight lines, think about simplicial complex not just as a formal definition as I gave before, but simplicial complex as edges, triangles, etc. If I take a map from the vertices, there is a unique way to continue it in an affine way, to straight line, triangles, etc. The geometric overlapping property tells us that if we take this affine extension, there exists a point z in R to the d, which is covered by epsilon fraction of the images of xd. xd is the set of d-dimensional simplices. So the Bharani theorem that I mentioned before means that if we take the complete d-dimensional complex on n vertices, namely we take n vertices in an abstract way, we take all the edges, all the triangles, all the faces of dimension at most d. This is the complete d-dimensional simplicial complex on n point. D is fixed, n is going to infinity. Then Bharani theorem is exactly the statement that this family of d-dimensional complexes have the epsilon, the CD in this notation, geometric overlapping property. What Gromov proved that they also have the topological overlapping property. Now think about it. That's a much stronger theorem. It tells you that in any way you extend the map from the vertices to the simplicial complex, you still have this property. So Gromov says that these complete simplicial complexes where d fixed and going to infinity also have CD topological overlapping property. In fact, Gromov proved it with a constant CD, which was better than the constant which was known before for the affine case. So he proved a much stronger theorem with a much better constant. It's still an open problem what is the real behavior of this CD. Let me just that you see how non-trivial is this theorem of Gromov and even counterintuitive. It's really counterintuitive. Can you please operate the video now? I don't know anything about that, but I asked somebody who is expert on animation to prepare a little video. Can you please operate the video? Oh, let's see. Good. So you see here we have 8 points. 8 points, well, n choose 3 is already 56, I think. So we are going to have 56 affine triangles, right? Just triangles. And we will see very soon that, there will be some area which is heavily covered by many of the triangle. So, of course, we are not going to count exactly here, but you'll have to believe me. Anyway, to be honest, when you do it with 8 vertices, it really means nothing. But you see, this area is covered by many triangles. But this is nothing. Let's think about the situation in the Gromov theorem, which allow you to put the edges in any way you want. In particular, you can make all the triangles to be extremely narrow. Moreover, you can kind of escape. Let's say that you apply the Bharani or the Boros theorem, Fourier theorem, and you know where is this area that many of them meet. You can completely avoid this area, that none of the triangles will come there. You can make them so narrow to escape to some place, to some other place, right? That's exactly what this picture is doing. You know, we take them all the way to the left, and the theorem of Gromov tell you that you will never escape. Well, you escape from that, but you will be caught in another corner. Still, 2/9, the same number, 2/9 of the triangles will meet at some point. It's kind of really amazing. And you see, this is the old one, and the green is the new one. And they are completely different. So it's not because of Boros-Fourier theorem. And they still meet each other, you see? They meet in Brazil instead of meeting in Israel. Anyway, let's go to our story. Now, just an hint, still, why Gromov theorem is at least can be correct. You see, once you put an edge, on the same edge, there are many triangles. If you want all the triangles to be small, you cannot regret. You cannot change the drawing of that edge. All the triangles should be if you want all the triangle to be very small, they all have to be very close to that edge. So somehow you concentrate many triangles to that corner. And in a way, that's what makes Gromov theorem correct. The proof is quite fancy. It uses cohomology and that. It's not elementary proof. But Gromov put the basic question because of that intuition, and in fact, okay, maybe before that, let me say now, before I say what is Gromov problem, let me explain now why all this is connected to expanders. What's the connection between this and an expander? Let's go back to the one-dimensional story, the one-dimensional situation, and assume we start with an expander graph. Take the case dimension 1, and let x equal VE be an epsilon expander. So you remember, this is just a graph such that from every subset, there are many vertices many edges which are going to its complement, right? Now, I claim that expander graphs have the epsilon topological overlapping property of Gromov. Why? Think about, you have a map from the vertices to R, to the 1, right? This is D equal 1. Pick up a point R such that half of the images are below that point, and half of them are above. And let A be the set of vertices which are, say, above the point Z. And A bar, A complement, are those which are below. Each one is approximately half of the points, right? Now, I take a continuous continuation of this map to the edges. Every edge from A to A bar must cross Z by what is called intermediate value theorem, right? A map a continuous map which take you from a point up there to the point up there must cross the point in the middle. And expander is exactly the property which tell you that there are many edges going from one set to another, no matter what is the division. So you can see that expander graphs have this topological overlapping property. So now let me just recall. Now let's go back to what we said at the very beginning of this talk. The fact that the complete graph is an expander graph, it's a triviality, it's an uninteresting statement. The fact that if you take the complete graph, the whole point of all the theory, you know, I add the slides with the random method, with the property T, with the Ramanujan, with the zigzag, with the interlacing polynomial. The whole point was, the non-trivial issue was to prove that there exists expander graph of bounded degree, K regular graph, where K is fixed. The fact that the complete graph is an expander is triviality. Now go to the higher dimensional case. The fact that the complete simplicial complexes are geometric expander is the theorem of Bharani, which is non-trivial. The fact that the complete simplicial complexes are topological expander, namely they have the topological overlapping property, is a very deep theorem of Gromov. So Gromov asks, are there at all, for a fixed D greater than 1, are there at all geometric or topological expanders? Namely, what he wants, let's say, he didn't formulate it like that, but in retrospective, that's the way we formulate it now. A family of D-dimensional simplicial complex will be called geometric expander, respectively topological expander, if all have the epsilon respectively topological overlapping property for the same epsilon. And the basic, so as I said, while it's trivial to prove that the complete graph are expander, the higher dimensional case of complete complexes is highly non-trivial. And Gromov posed in 2010, are there bounded degree geometric or topological expander I-dimensional? Are there at all? Shortly after that, it came a paper in 2013 of Jacob Fox, Gromov himself, Laforgue. Now this time is Vincent Laforgue, not Laurent Laforgue, the brother. And Asaf Naor, who will speak tomorrow, I believe, and Janusz Pach. And they prove that for every D, indeed, there exists bounded degree. Bounded degree means every vertex is contained in a bounded number of simplices. There exists a bounded degree simplicial complexes of dimension D with the geometric overlapping. They gave two different proofs. They gave two different proofs for that. Well, in fact, they gave even more than two. But the main kind of method of proof, one was random. Just like random graphs give rise to geometric, expander graphs, they have a model of a random model. I won't go to details, but probably if I would tell you, find a model of bounded degree simplicial complex, you probably would suggest this model. That's the kind of the natural model for bounded degree, I stress, bounded degree simplicial complexes. I stress it because there are other models of random simplicial complex. There is a full theory which was developed by Lineal and Meshulam about random simplicial complexes, and they are different. They are not bounded degree. So they have bounded degree random simplicial complexes, And they show that they have the geometric overlapping property. Namely, they are geometric expander. And now, you remember I told you that the Ramanujan complexes will come up. And then suddenly they took out our Ramanujan complexes, which were constructed like 10 years before and been forgotten for a while, and said, these Ramanujan complexes are explicit construction of such geometric expanders. Good. So we were very happy, and I have to admit, I didn't know anything about all this theory, Borush-Furedi, Bharani, etc., but I was excited that they are using this, and I went to learn this. And of course, now what you want to say, they solve the problem of geometric expanders. But there is another issue of topological expander. In fact, I talked with Gromov. Gromov was not sure if topological expander exists at all. Because this property that you can, that topological is such a strong property, you can kind of escape from that. And the fact that you have only bounded number of triangles sitting on every edge may hint that that's a big difference. Gradually, we managed to answer this question in a very strange way. The natural guess would be, Ramanujan are so great. No, before I'll show you the next. Let me tell you, the random complexes the model of random complexes that they use in order to get geometric expander that satisfy the geometric overlapping property are not topological expanders. So you see, it really shows you that there is a big difference between being geometric expander and being topological. We understand that being topological expander is a so much stronger property because we want this overlapping property with respect to every continuous extension, not just with respect to the affine extension, right? But this shows you that random ones are geometric and are not topological. So it's a real difference between the two notions. It's not just a feeling that they are different. So here is the theorem. This was proved first just in dimension 2 by Tali Kaufman, David Kashdan, and me. And then Kaufman and my student Shai Evra extended this to every D. And here is the very strange theorem. You remember we walked over the p-adic numbers, or the field of formal power series over the finite field of order P. Fix P, but P should be very, 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 very large. But then we fix it. If we fix P, and we take congruent subgroup of arithmetic group acting on this Brouatis building, blah, 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 we are getting a sequence of bounded degree simplicial complexes. I tell you as a secret, they are bounded degree, but the degree is like 10 to the 100th. This is bounded, but it's not small. We don't know to do it with small number, I have to admit. But formally speaking, bounded is bounded, right? 10 to the 100th is also bounded. We are getting a family of bounded degree simplicial complexes, Ramanujan complexes, but we don't know that they are a topological expander in the right dimension. In dimension, you see, we take D plus 1 dimensional Ramanujan complexes. We obtain them from PGL D plus 2. If you remember, from PGL2, we get graphs. From PGL D plus 1, we get D-dimensional. We take D plus 1 dimensional complexes, Ramanujan complexes, which are obtained from PGL D plus 2. We don't know whether these complexes are D plus 1 topological expanders. What we do, we throw out the top faces. we take the d-dimensional skeleton. We take only the simplices of dimension at most d inside this d plus 1 complex. It's a kind of a strange way. And we don't know that that's the truth, that that's the best possible, but it's just that the method of proof took us there. And then we can say that this skeleton are indeed d-dimensional topological expander. Because we have infinitely many like that, this gives a solution to the problem of Gromov, but in a way is not the natural solution to the game. And it's still an open problem, is x d plus 1, namely whether the x himself is a d plus 1 topological expander, whether the Ramanujan complexes themselves are topological expander. This is still an open problem. Okay, I still have like 10 minutes, and which is better than I expected. But it's not enough to show you what I prepared. But maybe you are lucky because you don't want to see these technicalities, right? So I will just tell you the story behind this. And there is a nice story somehow which kind of lies behind the proof of these results. So and this is the notion. So there is another way to extend the definition of expander graph to an i-dimensional expanders, to i-dimensional complexes, which nowadays we call it co-boundary expander. Co-boundary is the map in the cohomology. We look at the simplicial complexes, and we look at their cohomology over the finite field of order 2. The people who really started that approach were Liniel and Meshulam. So there is a very nice story here. Let me just tell you it without going to technicalities. Liniel and Meshulam wanted to have an i-dimensional version of the classical story of Erdos-Renyi of random graph. You know, the theory of random graph was started by Erdos-Renyi like, I don't know, 60 years ago or so, even more. And it's now all over the places in computer science, in combinatorics, random graph are studied in great details. And they wanted to have notion of i-dimensional version of this theory to define random simplicial complexes. Now, as I hinted before, their notion was completely different than the notion of randomness of Fox, Gromov, Laforgue, Naor, and Park that I mentioned before. They said the following. How do you define random graphs by Erdos-Renyi? They take n vertices, and they take every edge with probability p. P is something between 0 to 1. This p can be fixed, but it can be also a function of n. The first question, which was studied by Erdos-Renyi, was when the random graph is connected. And they prove a beautiful theorem. They prove that there is a threshold. Ever since then, threshold is the key word in all this area. There is a threshold. If p is less than log n over n, then the graph is not connected. If p, the probability of an edge, is more than log n over n, the graph is almost surely connected. Very nice. Now, Liniel Meshulam said, we want a model of simplicial complex of dimension 2. Their model is the following. You take n vertices, you take all the edges, so n choose 2 edges. So this is not bounded degree. But this is a legitimate model. Then they said, I take every triangle with probability p. I put it in or out with probability p. Okay, what the first question to ask? Is this connected? Of course it's connected. Because I started with the complete graph. So everything is connected here. They said, no. Connectivity for graph is the vanishing of H0, of the first cohomology group, over F2. I will ask now about the vanishing of H1. If we study d-dimensional simplicial complex, the connectivity is the vanishing of the d-1 cohomology group. And they prove, first in dimension 2, and then Lineal and Wallach in every dimension, a beautiful threshold. That if you take the random model of simplicial complexes of dimension d, if P is less than d times log n over n, the cohomology does not vanish. Over that, the cohomology vanishes. That's a beautiful extension of the Erdos-Renyi theorem. All this is a beautiful story. The most relevant for our story is the notion of, they didn't call it, they didn't speak this language, but they really define something that nowadays we call co-boundary expander, which really express in the language of cohomology the Chigger constant in dimension 1 becomes this co-boundary expansion in higher dimension. Amazingly, the same invariant appear in the work of Gromov. Without, Gromov was not aware to their work, they were not aware to his work. He defined independently this co-boundary expansion. And you know, if two people, different people, came to the same definition from completely different point of view, it really shows you that this is a natural thing. So I don't want to do it because it will be too technical for such a talk. I just want to tell you that this co-boundary expansion, in a way, is a key technical ingredient in many of the works here. Because what Gromov proved, that if this co-boundary expansion, you can think of it as an higher dimensional version of the Chigger constant, is positive, is bounded away from 0, then this implies topological expander. This implies this overlapping. So this is the key ingredient to prove his theorem about the complete graph. And what we did was adapting this to the Ramanujan. This was a little bit more complicated because the Ramanujan, the Chigger constant, can be 0 for Ramanujan. So we have slightly also to extend it's too technical to explain here, but I just want to say that the cohomology mod 2 plays an important role here. Cohomology over R, by the way, is also interesting here, and this is, in a way, the right generalization of the spectral gap business. But for graph, spectral gap and expansion are essentially equivalent to each other. In the higher dimensional case, we know that they are not equivalent. That's exactly the difference between cohomology over characteristic 0 and cohomology over characteristic 2. So there is something here which this little innocent object like spectral gap of a matrix and expansion of a graph suddenly, in the fancy language, giving you different type of notions which are related somewhat but are not really equivalent. Anyway, one of the good news is that suddenly this area got a push, and in recent years even found applications to computer science. So believe it or not, in the last year or two, there are many computer scientists who are learning cohomology, because it turns out that this co-boundary expansion is important to a subject which is of fundamental importance in computer science called property testing. Some of you may hear this PCP theorem, which is the provable checkable proof, which is maybe the deepest theorem in theoretical computer science. And this property testing, which is an area of a great theoretical importance, but even with many application to error correcting code, etc., is very much connected to this, and suddenly there is a lot of interest in that. But I think I will skip these technicalities. I want to go, here is the little story I told you about the Erdos-Renyi and lineal Meshulam. But I want to finish up with some open problem, one or two concrete problem and one kind of philosophized problem. The concrete problem is that I mentioned before, are the Ramanujan complexes themselves topological expander? There is this notion of bounded degree co-boundary expanders, and I mentioned that we don't know if they exist or not. Somehow we have a twist of this, which was enough for us to get topological expander. But really what I want to say is the last, this will be my last words here. Is there a random model that will give co-boundary or topological expanders? You remember I mentioned to you that the model of Fox, Gromov, etc., of bounded degree don't give it. You may say, okay, let's try to look for another one. Well, I tried. I couldn't find. It doesn't mean much. But I start to think maybe there is a philosophy here, that maybe there is a reason, and maybe there is no such. Think about the people who are familiar with the work of Mostow and Margulis on rigidity know that there is a huge difference between rank 1 and higher rank. In rank 1, in Riemann surfaces, there is a Teichmuller space. There are a lot of surfaces of small dimension. When you go up, suddenly the only cases are the arithmetic one. That's the Margulis arithmeticity. Moreover, the congruent salvo property, if you want the Serre conjecture, tell you that even within them, only the congruence quotients exist. Namely, they are very few, they're all gems coming from number theory. Maybe there is a similar story here. There is a rich theory of bounded degree graphs with a beautiful structure in dimension 1, and maybe there is no such rich world, only gems like the Ramanujan complexes, which are fantastic and deserve a lot of study, but maybe there is a reason that there is no deformation space of such complexes. And this is, the future will tell us what is the truth here. Thank you very much.
Thank you, Professor Lubotzky, for an exciting glimpse into higher dimensions and the connections with topology and arithmetic. I just had one very quick question. Is there a quantitative version of how large the overlap set is when you look at these overlappings?
Absolutely. All the results here are quantitative, but they are embarrassing. That's why I didn't say. The constant epsilon, the degree is 10 to the 100, and the constant is 10 to the minus 50 or something like that. So there is a lot of room for improvement here. As of now, we are only just at the beginning of this theory. So there was a good reason for me not to stress this.
Well, the harder they are to find, the more exceptional and interesting they'll be when we find them, I guess. Unfortunately, in this venue, it's not really possible to take questions from the audience, but I believe Professor Lubotzky would be willing to speak with people individually or privately after this concludes. I'd like us to thank Professor Lubotzky again for a stimulating, very exciting lecture.
Thank you very much.
This concludes our session for our first plenary speech of the day.